All right, so yeah, before we really start, I may just have a few words here. So I welcome to this course, and my name is Dr. Yongquan Ye. I'm working in the Department of Radiology, and I will take over this course until the end. Dr. Shabir Habib was supposed to be giving you his sections on chapter 23 and 24, but he has some conflict in schedule, so he cannot make it, so I'll take over his sections too. So by now, you have taken how many sections? Like 13, something like that, 13, 14 sections. So I assume that you guys have already been introduced to those basic concepts in MRI. And from today on, those sections, the new sections, will be more like using those basic principles and equations into practical applications and practical more, some real life examples. So there would not be too many equations, but still there will be some important equations that I will show you, some deductions. But more importantly, I would like to introduce those concepts by giving you some examples, some real life examples. So I think I hope that I can make a MRI learning interesting course. Okay. So has any of you guys find MRI course interesting by now? Okay, one. Good. That's good. All right, so today's topic is chapter 18. So it's fast imaging in the steady state. So the keyword here is the steady state. So that for fast imaging, we have a lot of other techniques, very interesting and very complicated techniques to achieve fast imaging, but not necessarily in features in steady state. So the keyword today is to understand the steady state signal characteristic and how we are going to analyze those with different situations. So previously in MRI, so you guys have already been introduced to these concepts. So these are those related to this section. The first one is the MR signal detection introduced in chapter 8. And then it's the concept of T1 and T2 and T2 star decay, and the gradient echo and spin echo also in chapter 8 and chapter 12 maybe. And also the most important thing is the T1 weighted contrast concept that was introduced in chapter 15. So there are also other related topics. For example, like the RF pulse in chapter 16. If you are interested, you should also review those chapters to better appreciate the concepts that is introduced in this chapter. So today's content is mainly three parts. The first part is to introduce the SHOT-TR, spoiled gradient echo imaging. Then the second one is the SHOT-TR coherent gradient echo imaging. And the last part would be to understand the spoiling mechanisms for the first part. Okay, so a little bit review of the concept we have already learned. So when we have done a signal excitation, we have tipped the magnetization from the longitudinal direction into the transverse plane. So afterwards, then the signal will start to recover along the longitudinal axis towards the parallel direction to the external field. So the rate of this recovery is described by T1, right? And then the signal that is located in the transverse plane will slowly decay until 0. So this decay rate is described by T2 or T2 star if there is a few inhomogeneities. So when we are talking about T1 and T2, sometimes we just just say, okay, it's T1 and T2, and there is this plot in the book that describes this dynamic process after the magnetization was tipped into the transverse plane. But actually, there is some problem with this figure. It will be a little bit misleading. Why? Why is that? So when we are thinking of T1 and T2s, or T2 star, we have actually need to understand the fact that the T1 is actually independent of T2. So there is no necessary correlation between T1 value or T2 value, or the process between the T1 recovery and the T2 decay, because we know that their mechanism is totally different. So the T1 process is actually the interaction between the spin and its environment, which is the crystal lattice, right? And the T2 is actually the interaction between spin and spins. So they are actually it's two totally different process. So when we are talking about the T1 and T2, we have to specifically say that the T1 only applies to those to the magnetization components that is parallel to the B naught, the external field. And T2 or T2 star, they're only applied to the magnetization components that is perpendicular to the B naught and V1. And actually, if we will be seeing this in later parts of today, actually the signal phase history of this these two type of magnetization components, they will be totally different. So you cannot just simply sum them up as two identical vectors and do this dynamic process. So it may be true. This one may be true only for the initial, for one single RF pulse. So if you just tip the magnetization, the equilibrium magnetization to the transverse plane and let it freely decay and recover, this is true. But if you applied multiple RF pulses, and this is a little bit misleading. So we need to understand that. Okay. So in terms of MRI data acquisition, we have known that the data we collect from the readout is used to fill the K-space. So there are multiple schemes to fill the K-space. The most often used one is the Cartesian. So we fill the K-space using the phase encoding lines, line by line, right? And there is also a radial acquisition and spiral acquisition that we can briefly mention, but it's not the total focus of this course. So the context of this chapter will focus on the Cartesian K-space filling, and why would we need fast imaging, right? Of course, faster is better, always better. So we can get a shorter scan time. We can reduce the motion-related artifacts. We can reduce the discomfort of the patient or subject that is lying inside the magnet. And also, it will save money to the hospital or get more money by doing more cases, right? And also, sometimes when you do fast imaging, some specific image contrast can only be achieved by using fast imaging techniques. So this would also be a consideration when we are using the, yes?
So in fast imaging, we acquire the data quickly or we acquire less number of data?
Well, if you only talk about fast imaging, both cases would apply. So, and even if by collecting less phase encoding data, it will also alter the it will also possibly alter the image contrast. So normally, if we're looking at a Cartesian acquisition scheme, how do we achieve the fast imaging? So we know that this total acquisition time is proportional to the multiplication between the TR, the repetition time between the different two excitation pulses, right? And the number of phase encoding, and in the case of 3D imaging, the number of partition encoding. And also there would be some kind of turbo factor, which is not introduced in the book, because back then there were less choice of fast imaging techniques. So now usually there will be a concept of turbo factor introduced, which would be, for example, if we collect a multi-echo sequence, then it will immediately increase the scanning speed by n-fold. So in this chapter, we only focus on the shortening of the TR to achieve the fast imaging. So, okay, so when we have now applied a rapidly repeating excitation because we want to shorten the TR. So the TR definition in most cases are the interval between two identical excitation pulses, right? So when we rapidly applying to a series of RF pulses for the excitation, this will lead to several conditions. The first one is that the longitudinal magnetization, they do not have enough time to fully recover it due to the T1. And also the transverse magnetization, they do not have enough time to fully decay to zero. So there will be, so at the end of this short TR, there will still be a non-zero or non-equilibrium magnetization before each excitation. So this status would then be the initial state of the next excitation pulse, which would be different from the equilibrium. Okay, so there are two concepts about the steady state. So the first one is the incoherent steady state, and the next one, the other one is coherent steady state. So what is the incoherent case? The incoherent scenario is that the residual transverse magnetization is destroyed at the end of each TR, or just right before each excitation pulse. So that means every excitation pulse only affects the longitudinal magnetization that is left at the end of the TR. So here is several cases. Okay. So here are several cases. This is just the simplest scenario. We just applied a series of 90-degree pulses with a certain interval, TR. So what happened is that before the first 90-degree pulse, we have the equilibrium magnetization, so which is pointing parallel to the external field, right? So after the first excitation, the 90-degree, we have fully tip all the magnetizations to the transverse plane. So there is nothing left in the longitudinal direction. And then it will just slowly grow back. Just slowly grow back due to the T1 recovery. And it's also the same. Similarly, it's also for the transverse magnetization. First of all, it will have all the magnetization tip to the transverse plane. So we have the initial magnetization as the same as the equilibrium. And then it will start to slowly decay due to the T2 or T2 star decay. So, but because the TR now is, let's say the TR is smaller than T1, so there is not a fully, there will not be a fully recovered recovery of the longitudinal magnetization. So when we apply the second RF pulse, it only has this much to excite. So it will repeat this process again and again and again. It always recovered from the zero. And then for the transverse magnetization after the second RF pulse is now less than the equilibrium, and it will stay the same if we are applying the 90-degree pulses. So this process would be similar if we apply a RF pulse with a smaller flip angle, but it would just take a longer time to reach this steady state. Also, for any sequence, basically for any sequence or MRR methods, we can say that if we just want to collect them fast enough, it will reach a certain kind of steady state. So this is the same. This is the spin echo. If we use a very short TR, we still have the very similar result here. This is the inversion recovery, which first applied the 180-degree inversion pulse and then excitation pulse. So if we only have a small enough, short enough TR, it will also achieve some kind of steady state. So let's take a quick look at how we can estimate these steady state signals. So let's say we have already reached a steady state, and okay, let's say this is just for the simple gradient GRE sequence. We applied a series of RF pulse with theta flip angle. So assume we have reached steady state. So before the, for example, before the nth RF pulse, and according to the definition of SSI incoherent, we will say that before the transverse magnetization before this RF pulse, it will be smaller to zero. And then we write down the expression for the longitudinal, which is the one we want to calculate. Okay, and then after the nth RF pulse, which has flip angle theta, then we will have flip this magnetization by the angle sine theta to the transverse plane. And what is left in the longitudinal axis would be this one multiplied by the cosine theta. So this is a very simple concept. And then during this, the TR, after this RF pulse, there will be T2 decay on the transverse plane. There will be T1 recovery on the longitudinal axis, right? So this was the one we see in the chapter 8. Okay, so just at the end of this repetition, we have this the transverse magnetization would have decayed according to this according to this E2 term, and then the longitudinal magnetization would have recovered by this much, according to the E1 term, right? So which is the correlated with the TR. So since it's at the steady state, so this one would be exactly the same as the last one, and we would have then we will have spoiled this transverse magnetization to zero by means of gradient and R pulse. We will see about that later. So by solving this simple equation, we will come up with the steady state incoherent signal for the gradient echo or the FID signal. So this one is in this form. So we can see that immediately see that it's the function. First of all, it's the function of the photon density, is the function of the T1 and is the function of the TR. And also, it will be the function of the flip angle. So it's actually affected by these 4 different parameters. So this one is not, it's the intrinsic property of the tissue. So we can just put it here. So what we can control is the TR and the flip angle. Okay, so we have a quick question. What do you think the SSI for spin echo? Spin echo is this one. So what do you think the SSI signal? What do you say? Yeah, basically it will be exactly the same. Yeah, exactly the same. And the second question is, how about immersion recovery? I'm sorry, which one? The immersion recovery? Yep, so that's a little bit more tricky. It's not the same as this one. So, but for the spin echo, it will be the same. All right, so this is the longitudinal magnetization that can be used for the excitation. So what we can get for the echo signal, if we collect it using a gradient echo, we can get this. This is the signal intensity we can have. Is the function of the is this term multiplied by the flip angle sin theta, and then there is the T2 star decay associated with it. So the popular sequence for this steady state incoherent is one is the flash, the fast low angle shot sequence, and the other one is the gradient echo sequence. So basically when you see these two, you know that they are using the steady state incoherent mechanism. So you can use this equation to estimate the signal intensity you will get from the from the parameter you are setting. All right, so let's say this this is the transverse magnetization that we can get if from this SSI signal if we are using a flip angle of theta. So let's just assume that we have a very short TR, so it's much shorter than the T1, and then we have a very small flip angle, which is much shorter than the Ernst angle. Oh, I should have said Ernst angle sooner. So Ernst angle is introduced in the next slide. So let's say we know the Ernst angle. Ernst angle is the angle that you can obtain the highest signal given the T1 value and the TR value. Okay, so if we have a very small, so the indication that if we have very short TR and very small flip angles, then we can get, we can see that the signal intensity is approximately proportional. Excuse me. It's proportional to the proton density weighting and the flip angle itself. So if we have a flip angle less than 1/3 of the Ernst angle, so that means this term is less than about 0.1, 10% of this denominator. So we can consider that the theta is small enough. So we call this a small flip angle imaging. So in small flip angle imaging for gradient echo, the images, they are proton density weighted, mainly proton density weighted. And if we have a very short TR, but we have a very large flip angle, which is, for example, if it's close to 90 degrees, then we can we can see that the excited signal is proportional to the TR to this term, which is the M naught TR over T1. So this is proportionally related to the TR we use. But of course, this has to be a very short TR. So in this term, we can see that it's T1 weighted. So if you have a longer T1, you have a smaller signal. So this is just a simple, a more simplified version. So when the flip angle is not 90 degrees, it is still heavily T1 weighted, just not as this clear. Okay, so yeah, this is the introduction of the Ernst angle. So Ernst angle is the flip angle that when you have given a certain TR and T1, is the flip angle you can achieve maximum signal for that specific tissues. So its calculation is easy. The calculation can be the when the derivative of this equation to be 0. So you can calculate that and come up with this conclusion. And when the TR is much smaller than T1, you can probably have this estimate of flip angle, which is the square root of 2TR over T1. But remember, you have to use a very short TR already. So we can, here are some typical T1 and T2 values of the tissues, the brain tissues. So here is the signal intensity cos as a function of the flip angle. So we can see that for the gray matter and white matter, they have a slightly different Ernst angle because they have different T1 in here, right? And if we take a look at in this one is just a zoomed version of this plot. So it only shows a small flip angle range here, up to 30 degrees. So we can see that for very small flip angles, probably just a couple degrees or 0 degrees, we can see that this part is almost linearly proportional to the flip angle, just as we have predicted before, right? And in here, so it's just directly proportional to the spin density. So at this region, when we use very small flip angles, we got photon density weighted imaging. Okay, so here we can, if we compare the signal difference between the gray matter and white matter, we can see that just very soon after the Ernst angle, we can see that the signal differences are basically very similar. They kept very has been almost constant for a wide range of the flip angles up till 90 degrees. So that means at this part, just above the Ernst angle, we can get a relatively constant T1 weighting in the images. So the indication of this that most of the time we don't need to use a very high flip angle to achieve a good T1 weighted image. And also on the other hand, if we use a high flip angle, we actually got lower signals. Although the contrast between the gray matter and white matter, they remain the same, their signal, their absolute signal would decrease. So we got a worse SNR in the images, but constant contrast to noise ratio, constant CNR. And of course, if we use a flip angle of 180 degrees, we can see that they all just flip back and forth along the longitudinal direction. So we would expect that to be 0 signal. So that it will also prove that this this plot is correct. All right, so this is a quick look at the contrast to noise of ratio of the SSI signal. So if there is T1 differences between the two tissues, if it's not too large, then we can estimate the contrast between these two kind of tissues. So if we have a small T1 differences, we can come up with this expression, and then we do, it's very complicated, so we want to see the maximum of this. So we do a derivative on this and take the 0, and we can get that the optimal flip angle would be 2E1 minus 1 over the 2 minus E1. And if we also throw in the condition that the TR is very small, then we can come up with an estimate that is the optimal contrast between two tissues with different T1s would roughly about the square root 3 of the Ernst angle of one of them. But of course, we have to keep in mind these conditions are here. So here is the simulation if we have two tissues with different T1s. So we can see that for higher T1 differences, we can definitely get a higher contrast between these two signals. So that makes sense, right? So the indication is that if we manage to decrease or increase the T1, well, most favorably is to decrease. To decrease the T1 of one tissue, then we can successfully increase the contrast of this specific tissue relative to others. So the application of this idea is that is the contrast enhanced MR angiography. So if we inject a contrast agent which can decrease the T1 of the blood, significantly decrease it, so we can have a much larger T1 differences between the blood and the tissues, and then we can now increase the contrast between the vessels and the tissues, and we can now better review those vessels. So about this MR angiography, we'll be talking about it in chapter 24. Okay, so here are some examples that we collected on our 040 MRI scanner, which is now already gone. Okay, so here is a flip angle of just 1 degree. So we can see that even with this, this is a very, very low flip angle, if you say. But we can still see a quite very good signal SNR in this image, despite the fact that it's only very small flip angles. We can see that, by the analysis we just went through, we can see that this one should be proton density weighted. So we have highest proton density in the CSF, so it shows the highest signal. We have second highest proton density level in the gray matter, so we are seeing the gray matter is has higher signal than the white matter here. So as we increase the flip angle here, well, first of all, because we can see that the CSF has already has the decreased signal, even with still a very low flip angle of 4 degrees, because CSF have very, very long T1 value. So its Ernst angle is very small, right? So it might have already reached, the Ernst angle might have already been passed if we use the flip angle of 4. It might just be 2 or 3 in this case. So if we increase the flip angle furthermore to 8 degrees, we can see that CSF has become dark now, because it's now suppressed due to this T1 saturation effect. So when we call when we call that the signal of the tissue is being suppressed because it's long T1, we usually call this as a T1 saturation effect, but it's actually just a simple SSI signal. And now at this point, we are seeing very minimum contrast between the gray matter and white matter. Now, because at flip angle of 8, we are approaching the Ernst angle of both the gray matter and white matter, because they are very close. The T1 is very similar, so they have very close flip angle. So when we have we are approaching this Ernst angle, then we have minimum contrast, as we see before. And when we go higher and higher, we are now getting more and more T1 weightings into the images. So for the T1 weighting, we can see that flip angle, the CSF is become very dark. We have because the gray matter has longer T1 than white matter, then it also has a lower signal because it's inversely proportional to the T1, right? Okay, so when applying a series of RF pulse to achieve this steady state, we actually we understand that we should require a field repetition of these RF pulses cycles so that the magnetization will reach the steady state, right? If it's not the 90 degree. So we have analyzed the number of RF pulses needed to reach the steady state if we are using the Ernst angle. So this would be shown in here with this expression is basically is the T1 over the 2TR. Alpha here is the target relative error. So if we want to make sure that the variation of the signal is small enough so that we can correlate a steady state. So if we so from here we can say that if we use a flip angle of 0, then we naturally need infinite numbers for it to reach steady state, right? And if we have flip angle of 90 degrees, then we only need 1, and then we can immediately achieve the steady state. So this is the two simulation to showing this how many RF pulses needed if we have different imaging parameters. Here is a short TR with 40 milliseconds. We can see that it requires approximately 30 repetition of the TR before the gray matter and white matter reach the steady state. But if we use a much longer TR, we can see that we only require a few repetitions for the gray matter and white matter to reach the steady state, right? So it's so that means if we use a shorter TR, we need to give it at least still give it sufficient time to reach the steady state. So in this case, let's say this is 30. So we actually need like 30 by 40 milliseconds. That's about 1.2 seconds for it to reach steady state. And here is for let's say it's like 10. So we still need 4 seconds, 4 seconds for the signal to reach steady state. So that depends on the parameter you need. Okay, so so since this is still a little bit long, right? 1.2 seconds or 4 seconds. So we need a couple seconds to practically wait until the brain tissue signal reach the steady state. So we need to take into consideration several factors if we collecting this this part of the signal before it's reaching the steady state. So first of all, we need to consider that whether we are doing a 2D or 3D imaging. So let's say it requires 100 TR, 100 repetitions before it reaches steady state. So for 2D imaging, if we are acquiring, for example, 256 phase encoding lines. So that means almost half of the K-space is in an unsteady state. But for the 3D, we are actually collecting, for example, like 256 by 128. So that means only a small fraction of the phase encoding lines in the whole K-space is in this unsteady state. So the effect of this signal of this unsteady signal would have very different portions in the 2D or 3D space. So we need to take into consideration that. So if for 3D, so the indication of this is that for 3D, sometimes we can just immediately collect the data, regardless it has reached a steady state, because those unsteady state signal would have a very small contribution to the whole K-space. But for 2D, we probably would need to wait until the signal has reached steady state before we start collecting data. Right. So also, if we collect these signals, it will also it will cause filtering effect in the K-space, right? Because it's decaying. So in the K-space, if we collect it and put it into different lines, that we are actually like imposing a filter into the K-space. So that would lead to a certain kind of blurring. And also, this would also cause different kind of T1 shine-through effect. So if we want to collect proton density weighted imagings, this kind of T1 shine-through would actually increase the T1 weighting into that image, so that you may get a wrong readout of the proton density. But on the other hand, it may also help enhance the edge information if we use this higher signal, with this higher signal portion to fill the edge of the K-space. It might, actually help enhancing the edge information for high resolution imaging. But most of the time, this may not be the case. So practically, people usually do not acquire this part of the signal for 2D imaging. And also, of course, we can get a quicker scan. We don't have to wait another 2 or 4 seconds before collecting. So if we are collecting like 20 slices, this delay would cost us like a couple minutes. So this would also make a very significant difference. And okay, so how about we? To deal with this problem, there may be some. We can also use the force constant magnetization. So we just applied a various flip angle, so that the magnetization we see is immediately appearing at the same steady state. So so this one is actually yes. Sorry. It's okay. 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 So yeah, there is this force constant transverse magnetization technique. So the idea is that to use a variable flip angle, so that the first field, the transverse magnetization that was excited by the first few RF pulses has the same magnitude as the steady state. So so that we can already immediately start collecting the data, regardless it has reached the steady state. So this is an example of the space sequence developed by Siemens. So it's basically a turbo spin echo with variable flip angle. So the variable flip angle, it has to take into account the T1 and the T2 and the TR of the tissue and the parameters. So here are several different schemes that is provided by this space sequence. So this is the flip angle, and this is the x-axis is the number of the RF pulse. So we can see that the RF pulse, the flip angle of the RF pulse is a function of its number. So corresponding to these different schemes, we can clearly see that, well, not quite clearly here. Yeah, maybe you can see it more clearly if we put it into the PDF. We can actually see a very, let me see. Yeah, it's not clear. We can see the difference in the vessels. We can see a very different representation of the vessels in this knee. So, yeah. Yeah, maybe we can take it over later. Okay. So we have now introduced incoherent steady state sequence. So is there any thoughts and questions? Okay. All right, so the next steady state category is the coherent steady state. So in contrast to incoherent, the coherent is actually keeping the transverse magnetization that is, at the end of each TR, so that this residual magnetization would also contribute to the following excitations, so the following signal TRs. So there can be different schemes of reaching the coherent steady state. So here are two typical ones that we usually see. So this one is we only have this coherent magnetization along the z-axis and along the y-axis. So if we, for example, this is the initial state before the excitation, and then we apply an excitation, it will tip the Z component of this Z component of magnetization. Part of it was tipped to the transverse plane. Part of it was remained in the Z-axis. And for this transverse magnetization, we also tip it because the RF pulse tips everything. So part of this transverse magnetization is tipped back to the longitudinal axis. But part of it still remains in the transverse magnetization. So we can have, so immediately after this RF pulse, for now, we can have a magnetization only along the y-axis if the flip angle has a 45 degree, right? But there is zero magnetization on the z-axis because they cancel out, right? And then during the TR, the Z component recovers and the Y component decays. And at the end of TR, it will become the same as its initial state. So this goes back again and again. So this is a more complicated one. It involves the magnetization along each axis. So you can take a good look at this. And actually, this so we can see that immediately see that actually the formation of this coherent steady state is actually depending on how you applied the RF pulse. So the RF pulse would have this very important effect. So the frequency of the RF pulse would affect which part of the off-resonance effect would have. The phase of the RF pulse and also the strength of the RF pulse will also affect the steady state. And also the gradient, we will see that later. We can either use a balanced gradients or imbalanced gradients to achieve different spin phase pathways. And also the timing to apply the RF pulse and to apply the gradient, they are also of critical importance to forming different kind of coherent steady state. Okay, so now because the signal from one TR is actually will be contributing to the signals in the subsequent TRs. So we have to be able to describe how the signals evolved during this TR. So we use this the total precession angles of this transverse magnetization components during each TR. So this is what we call the resonance offset angle. So this is actually to describe the total effect from the, for example, the field inhomogeneities, the off-resonance frequency effect from the RF pulse, and possibly if there is some different type of tissue like fat and water, we have also considered the chemical shift effect. So this would be contributing to this off-resonance offset angle. And also, if we apply the gradient, we need to apply gradient to enable to read out to phase encoding, right? To partition encoding to do the actual imaging. So when we are applying the gradients, it will also create certain kind of a controlled kind of field inhomogeneity. So this would also contribute to this resonance offset angle. So so if we do not want this resonance offset angle to be affected by the gradient, because the gradient is just a means of the for the imaging, for the spatial encoding of the signal, right? So it has nothing to do with the signal, the tissue property itself or the field inhomogeneity. So we actually want to have, we don't need this term. So it will, practically we would be setting this term, the whole term, the gradient moment, which we can say is the sum of the gradient moment, to be 0 during each TR. So here is the sequence diagram of the steady state free precession. So we can see that now we have a series of RF pulses with a theta flip angle. We have, so between each excitation pulse, we can see that the total area under all the gradients, they will have a sum of 0 in here. So that we call that. So when we have a zero value for this gradient term, we can call that the signal is being free precessing during this TR here. So what is reflected in this resonance offset angle is purely from the property of the tissue itself. And just as a side note here, there is different types of this steady state coherent. So here is the steady state incoherent signal of the gradient echo, right? We have this acquisition, we have this excitation, phase encoding, and readout here, and then we just have it open and we dephase the signal and something like that. So this is the basic gradient pulse sequence. And here is a graph sequence, or what we call FISP sequence. So we have extra phase rewinding here to to make phase encoding gradient moment to become 0 back. But we have an imbalanced gradient moment along the along the slice encoding and read encoding. So actually, this is collecting the so-called echoed. This will create a so-called SSFP echo. And we have another very interesting type of sequence that is PISF. So it's basically the inverse of this SISP sequence. So it's totally just inverse. It's very interesting. So it collects the FID signal in here. And if we balance this these gradients to make all the gradients moment sum to be 0, and we have this SSFP signal. So yeah, this is just a side note so that you know that there is different sequences associated with this SSI. So here is the expression for the SSFP signal. It's very complicated, so we are not going to go through this one. So here is just describing the magnetization components before the R pulse and after the R pulse. So by looking at this point here, only by looking at this term, we can see that because the x-axis, the magnetization along the x-axis is the same before and after the R pulse. So that means that for this detection, we are assuming that the R pulse is applied along the x-axis so that there is no tipping. Because the R pulse, the B1 field is parallel to this MX excitation, magnetization, so there is no tipping effect, right? So this is a very important, you should know this. This is a very important condition here. So we can also say that there is no R phase increment or alternation, because so we'll see that later, that if we do a R phase increment or alternation here, what would happen. Okay, so this is because this is a very complicated equation, so we can only do numerical simulations using the computer softwares. And here is the very specific, we can call it frequency response profile. So for the large flip angle, we can see that for different off-resonant spins. So this is off-resonant. For 0 here, it's on-resonant, right? Remember the beta definition. It's the delta B term, right? So if the delta B term is 0, that means it's off-resonant. That means it's on-resonant. So now, for the on-resonant spins, because we are, and also because we are applying the RF pulse along the x-axis only. So for the on-resonant spin here, we actually have low signals. So if we have a perfectly homogeneous field, and everything is on-resonant, and we apply this, and we only get very low signals out of it, even if we use a very high flip angle, right? But if we go a little bit further off-resonant, we can see the signal becomes higher and reach a platform over a wide range of frequency range. And this is the characteristic frequency response profile of the large flip angle SSFP. So we usually call this is the passband of SSFP. And we can see that the stop band, these stop bands, they take place at 2n pi of the resonance offset flip angle, offset angle. So including this on-resonance case. But on the other hand, if we use a very small flip angle here, we will observe not a passband, but relatively a stop band. In place of this passband. So sometimes we can see in the small flip angle case, we can see the passband actually close to the 2n pi resonance effect. So so this is very interesting. For large flip angle, the on-resonance spins may have very low signals. But for the small flip angles, the on-resonant spins may actually have very high signals. So this is a very interesting and characteristic phenomenon of SSP imaging. So this passband is also a periodic appearance when there is a 2n-pi resonant offset angle. So there is also a very interesting point to note is that there may be a possible nulling point at this 2n-pi resonance offset angle. So if we have a very long T1, relatively very long T1, so we can see that we can see here the signal has a very sharp drop here. So that means if in here, in this small region, a very small frequency change would actually give you a very, very high signal change. So people has tried to use this band to achieve the functional imaging, because what functional imaging does is actually the blood flow change. It would induce a local T2 star change. So this T2 star change is actually related to the local field inhomogeneity change. So if we collected this, put this band just right next to that cortex, and that T2 star induce a very small field change would actually give you a very high signal change. So people has done this, tried this already. So we have noticed that the x-axis here is shown in terms of the beta, the resonance offset angle. But a question to you guys is that what is the bandwidth of this platform? So what is the bandwidth from this point to this point? It would be just very simple. Okay, so think of that a little bit. And again, I'm showing here is that there is no RF phase increment or alternation, so that we are seeing the stop band right at the on-resonant phase. So here are some examples here. This is the figures from the book. We can see that this is the stop band we are looking at. This is the stop band, corresponding to this 2n-pi of resonance offset angle. And this is the high flip angle case. This is low flip angle case. And on another, and this is the cardiac imaging using the SSP. We can also see that at the edge of the imaging field of view, there is very significant field variations because the field is not very homogeneous at the edge of this SOE. So we can see that there are multiple bands. This is because there is a rapid field change in here, and that caused the resonance offset angle to change rapidly. Okay, so how do we change this resonance offset angle so that we can move this off resonant this passband to a place that we we want. Well, for example, if this is the brain and I want to see tissue here, but now at this with this setting, this is just located in a stop band, so we cannot see it. So how can we shift this passband to here? So the basic idea is just to use the RF pulse to give the RF pulse extra phase. So when the RF pulse has off-resonant frequency relative to the spins, it will actually equivalent to adding up it's part of resonance offset angle to the total of resonance angle. So this will actually effectively shift the passband, the whole frequency response profile along that frequency range. So if we if we use if we shift the frequency of that RF pulse so that it will lead to a 2 pi change. Lead to a pi change in the off resonance, in the resonance offset flip angle. Then we can totally shift the pass band just to the center of the stop band so that they overlap each other. So sometimes when people are doing this kind of imaging, they will collect 2 sets of images. One set is with no RF flip angle alternating, and so that we collect one set of these images like this, and then we alternate the phase of the RF pulse by 180 degrees, and then we can collect another set of images, and then we overlap them together and use the, for example, choose the highest point between these two, and it will give you a homogeneous high signal image, as if there is no off resonance effects. So this is a very cool idea, but the price is that you have to collect it twice. Okay, so it's the same here. For the SSFP, we need a number of RF pulses before we can reach the steady state. So practically, people are also using the variable flip angles to accelerate this process. So this is the practical, the actual SSFP signal that I've been running the simulation with. So okay, so the next part is let's see about the image contrast that we can get from the SSFP. If we have a very small TR, which is much smaller than T2 and T1, and from the that equation that we saw before, and we can finally come up with this expression. So we can see that it's basically a T2 over T1, because this T1 over T2 is now in the denominator. So it's basically a T2 over T1 weighted contrast. So this is a new type of contrast. So if we have chosen optimal flip angle, we can come up with even more simple expression of the imaging contrast. So this is the square root of T2 over T1. So the SSFP signal images would give us the imaging contrast based on this ratio. So in the human body, the CSF and blood, they have the highest T2 over T1 ratio, which is about 1 over 2, something like that. So that means the signal of the blood in SSFP would show the highest signal. So usually this feature is used to perform MR angiography so that we can see the high signal in the blood. And because it's fast imaging, the imaging speed is very fast. So we usually use it to imaging the heart. So this is the example. We can see that the blood inside the heart, they have a high signal, while the myocardial muscles, they have a lower signal, so that we can clearly see that the beating heart. And yeah, this is because the very high acquisition rate of this sequence. We can actually dynamically capture the movie of the beating heart. And this is float independent. All right, so the next one is the spin phase pathway. So this one is not on the, it's not a must-taught part, but I think that this is a very important concept that you should know about, and not only for the SSP, but also for the spin echo, any spin echo related sequences. So it will give you an idea of why and how we are using all those different phase alternating and crusher gradients and flip angle variation schemes in the SSP or the TS turbo spin echo sequences. Okay, so when we are performing, giving a single RF pulse, we usually just simply use its flipping effect. So usually it's just like a sine theta or cosine theta to calculate its, its longitudinal transverse components. But actually, in the microscopic point of view, for each spin, for each water molecule, for each spin, it's either, and it's like receiving the energy from the RF pulse. So it's either, have accepted the energy, or it's either not, right? So it's still, so microscopically, we can actually consider that this RF pulse has this effect on different spins. So for some spins, it will just experience like a 0 degree excitation. So that means the RF pulse does not affect these spins. For another part of the spins, they would like has experienced a 90 degree excitation. And for some other spins, they will also just like experience inversion pulse effect. So there is the weighting of this, or the number of these spins being affected by a RF pulse is, the weighting is given by these numbers. And so the effect of this equivalent effect is that the first one is not being affected. So if there is already, so if this spin is already on the transverse plane and is not affected, so this group of the spins, they will still precess as if nothing has happened, right? And so this is, so here is the phase spin pathways. So how do we look at this plot? So for example, this is the transverse scenario. So we already have this spin or this magnetization along the transverse plane. Then it will develop occurring time because it's perpendicular to it's perpendicular to the external fields. So it will develop a phase. So if it's not affected, so for the part of this magnetization that is not affected by the RF pulse, it will continue to grow. The phase, it will continue to develop in the same direction and the same rate. For those experience 90 degree pulse, then it will be flipped back to the longitudinal axis. So at this point, when it is flipped to the longitudinal axis, it's parallel to the external field. So that means its phase does not precess anymore, but still it has the memory of the phase it has developed before. So this one would be the one, this one is the one that been flipped by a 90 degree to the longitudinal axis. And for the next part is the 180 degrees. For those spins that experience 180 degrees, its phase, the developed phase, will be inverted. It will totally inverted. So it will be from flipped from the positive to the negative. And then, it will still keep developing. It will still keep developing as if because it's still perpendicular to the external field, and the magnetic moment is still the same. So it will still develop along the same direction, and when it reach the zero part here, it will create an echo. So this pathway is actually the spin echo pathway. right? So in here, the N here is just called a coherence level. So that means how many units of TR it has experienced. How many phase it has developed for different units of TR. So for example, N equals 1, that means this spin has equivalently developed a phase of 1 TR. And N equals 2, that means this spin has developed a phase that equivalent to 2 TR, right? Okay. So using this spin phase pathways, we can actually analyze how the echo is formed in spin, specifically is the spin echo, how the spin echo is being formed. So there is many possible echoes being formed. It's a very complicated, and we are only showing 3 echoes here. So the transverse pathway that can possibly develop in terms of the RF pulse number is the power of 3n minus 1. So this is a very large number. So if we add another pulse here, we probably could not be able to show it in one page. So, so the maximum echo number after the nth RF pulse, it would also be very large. So it's just 1/2 of the total available pathways. So the echo condition is that the coherent level has come back to 0. So for those who is always developing above 0, it will not form an echo. So this is actually more like a dephasing path. But whenever this phase is flipped by the 180-degree component of the RF pulse back to the negative coherence level, it will still develop towards the positive coherence way. And then when it passes through this the 0 coherent level, it will create an echo. So whenever you see that this development passes through this line, you can see an echo. Is that clear? Okay. All right. So yeah, just some implications. Those if you are interested, you can take a look at more about those concepts. But implication of this spin pathway analysis is that first we can use them on the Hans angle. So the Hans angle is the 90 degree plus a 90 degree. So this one is the Hans angle. So it uses the 180 degree components to refocus the single phase. Although it's not a 180 degree pulse here, but it still has a 180 degree component. So effectively, it can actually give you, if we do this analysis using just a single vector of the magnetization, you cannot get an echo here. But in fact, it does get an echo. That's because we can, even the 90 degree RF pulse, it will have an effective 180 degree component according to that analysis. All right. So there is another sequence called STIM. So it's a stimulation echo. So what we call here is that the stimulation echo is using the 90 degree component to store the signal phase. So the stimulation RF pulse is like this. Is first is excited by the first RF pulse, and then is restored to the z-axis by the second one. So the phase development is stopped, and it remains at it remains at the z-axis between the second and third RF pulse. And the third RF pulses would then tip this component back to the transverse. So equivalently, the phase developed between these two RF pulses is now refocused during this period. and then it will come up back, forming a stimulated echo, as we call it. And also, so this stimulated echo is actually a very if we only use this stimulated echo, we can use it to do imaging or sometimes MR spectroscopy. But in the fast spin echo, this one stimulated echo can actually correlate with the RF pulse itself, so that it will destroy the signal coherence. So it will actually introduce the artifacts in the TSC images. So in fast spin echo or turbine spin echo, we usually need to use to crush the 90-degree component of each those refocusing pulses. And also the SSP now is actually a mixture of all these pathways. So it's a mixture of all the pathways if we draw them together. All right, so a quick summary of the SSP. So first of all, it's a very fast sequence, scanning sequence. So typically we can use a TR of 5 to 10 milliseconds. So it's widely used in cardiac and abdomen imaging because this body part, they are always moving. You're breathing. The heart is pulsating, and also the MR angiography due to its high T2 over T1 contrast. So yeah, this is T2 over T1 is this ratio weighted, and there has been an argument in the development of SSP that whether the signal is more like a spin echo or is more like a gradient echo. So after a while, I still remember like 5 years ago, still there's papers published on arguing this topic. But nowadays, people are, I think, probably are just using the just treat it as its own rather than trying to explain it with spin echo or gradient echo. So we need to understand that if we want to get a high passband signal using the high flip angle, we probably would get a very high RF pulse deposition into the human body. So I have gone into the scanner to do a scan using the SSP on abdomen, and I have felt the whole body is being heating up, and I got sweaty inside the scanner. So it is that hot. And also there are several derivative sequences, as we said before. There is the FISP, PSIF, there's TrueFIS, Fiesta, something. So this is if you are interested, you can just look them up. Okay, so the last part is that's good. So the last part is the signal spoiling mechanisms. So it's actually very important if we do not totally spoil the signal in the flash sequence or the gradient echo sequence. If we'll continue into the next repetition of the TR, and we'll mix up with the signals, subsequent signals. So just like there is multiple signal phase pathways mixing each other, so there would be sometimes they would cause imaging artifacts. So because microscopically, for each TR, for each spin, it actually cannot be forced to zero except due to the T2 decay, right? So you can just modify its phase or directions by applying the gradients, RF pulses, but it really does not change back to the zero. So if we use the a very long TR, then we can naturally lead to a signal, lead to a zero transverse signal because of the T2 decay. So this is a natural spoiling. But usually if we use the natural spoiling, we we are looking at like an hour scan of one single sequence. So that's not practical. So macroscopically, if we have we've been able to modify the spins so that the spins were spread with different phases, and then they can add up to each other, and then their vector sum would become 0. So that means if that vector sum is 0, then it will not contribute to the subsequent signal acquisitions. So the means of signal spoiling are two ways. One is the gradient, and the other is using the RF pulse. So the gradient dephasing is actually very simple. By applying a gradient, we are introducing a field inhomogeneity, so that it's actually like introducing an extra T2 prime term, so that by this actually it's like reducing the T2 prime, so it's effectively reducing the T2 star. So by reducing the T2 star, we actually can significantly dephase the signal inside a voxel. So to completely dephase the signal from a voxel, we need that the spins from that voxel, the total phase dispersion of the spins in that voxel would become 2 pi, so that their vector sum would become 0, right? So this is basically the idea of the flash sequence. The flash sequence uses a very strong spoiler gradients after the data acquisition for HTR, so that it just totally spoils all the data. And the other thing is the other way is to do the RF spoiling. So RF spoiling is more like a special case of the SSC signal. So basically, it's still SSC, but it behaves like SSI. So it's the RF spoiling is to do the varying the phase of the RF pulses, and for different number of the RF pulses, so create an effective SSI signal. So this is the simulation of the gray matter, and we can see that this is the expected signal level of SSI, and this is the signal intensity if we vary the RF phase by applying this phase increment to the RF pulses. So we can find that there are two specific phase numbers. One is the 117 degrees and 123 degrees. So these two, they actually can give you the signal that is very close to the expected SSI signal. And it works very good for both the gray matter and the white matter. So this is the basic idea of RF spoiling. So if we do this, if we put this SSP and we change the RF pulse phase by this numbers, we can actually get a signal that behaves very similar to the SSI signal. So this is the basic idea of RF spoiling. So practically, we will apply both to a gradient echoes. So yeah, this is basically the sequence diagram of the product, the Siemens product gradient echo. So it employs both the RF spoiling and the gradient spoiling. So to achieve maximum signal dephasing, to achieve a very good incoherent steady state. All right, so here will be the homework, and just as I mentioned, and just for you guys for fun, if you can try to deduct the SSI signal for the inversion recovery FID, just for your. So next section we will talk about chapter 19. Okay, so Is there any questions?